Hello, good evening. We are in the 13th week, so I hope you're having a good weekend, good week. Can you all hear me? Can you type yes? Thank you. Okay, so the plan today is to go over a few topics. One is just a recap of Dijkstra'S algorithm. And also, we'll just briefly talk about implementation with a binary heap. And also, we're going to learn something very important today called Quicksort. Quicksort is perhaps the most generic, fastest algorithm that you can use. All right. So the basic idea of the shortest path algorithm, or the Dijkstra'S algorithm, is that we call it a single source shortest path. So what that means is that you are really starting from one vertex and then try to reach the other vertices. So you have a graph that you try to reach the other vertices. It can be applied to weighted or unweighted graphs. So if it's unweighted, then you just count the number of edges in the shortest path. If they're weighted, then you will count the distance, the shortest distance between two nodes. One of the interesting things about the shortest path algorithm that we've talked about is that it gives you like a unique way to reach other things. So, for example, this could indicate the paths of a tree. So we call that a shortest path tree. Maybe this is the one. I'm not sure. But anyway, so it kind of builds a tree from the vertex you are starting from. Okay. So let's see how many of you remember this now. Let me turn on the poll. Okay, so let's try to answer the question. Dijkstra'S algorithm is used to solve which problem? Is it the all pairs shortest path, single source shortest path, or network flow? Clearly, I may have given you the answer from what I just discussed, right? Anyway, so let's just let it go. It's really the single source shortest path, okay? So I didn't have to wait for everyone to respond. All pair shortest path is essentially an algorithm that's going to compute the shortest path between any two pairs. In this algorithm, in Dijkstra'S algorithm, you just pick one source and then you try to find the shortest path to all the others. Okay, so there's, and the network flow is a different type of algorithm. Definitely, it's not sorting Dijkstra'S algorithm. Okay, let's see if you can recall this. What is the running time of Dijkstra'S algorithm? Oops, let me just initialize the poll here again. Okay, so if you recall, the correct answer is A. It's the E log V, because log V is for the heap, because you have to find the minimum. If you recall, in Dijkstra'S algorithm, you're always taking the minimum from a set of things, and then you have to touch all the E's. If you really, I mean, there's another term, but E log V is the largest term. So the correct answer is E log V, because for each edge, you have to figure out where the, using the vertices, you got to figure out the max. Okay. This is probably another question here. Let me just initialize that. Okay, so the answer is B, heap. It's important to use, we don't use a stack or queue or binary tree for implementing a Dijkstra'S. It gives you the linear time with proportional that, right? So it's a heap. Okay, so here's an example. So in this case, what you see in red is what's called the shortest path tree. So if you start from A, it shows you the shortest path to every other node. Okay, so it's 6 to C and 3 to D, 5 to B, and 3 plus 4 is 7 to E. All right, now what we're going to do is we're going to try to do this in a different way. So let's suppose we choose D as our source vertex. So this is source. All right, and the lines without arrows means they are double arrows. So that means you got things going both ways. Okay, so you can go either way. That means it's like having two edges anyway. All right, so the way we are going to do this, like we did last time, so we write, one second, let me get my, B, C, D, E, and D is our source vertex. So when we start, the distance from D to D is 0. And all the other distances are infinity. So we're trying to find the distance from D to everything else, right? Okay, so the way the algorithm works is that you have all these things in a priority queue. So right now, D is the minimum of the priority queue. Everybody else is infinity, so it's very large, right? So what we're going to do is we're going to start from D and see where we can go from D, right? So which nodes can we update from D? You can type it in. Which there are 3 nodes that I can update from D. It's E, C, B, E, C, and B. Okay, so E can be updated to 4 because that's we're using the edge 4. Okay, and you came to that from D. So H2 is a D. And then B can be updated to 2. You came to that from D. And then we can update C to B5. You came to that from D. Okay, now, which one do we choose next to relax, like a vertex? It's going to be B. Okay, because that's the minimum distance in the priority queue. So we take B, the B, and then we try to see if we can go to A. Obviously, now I can relax A. But what's the distance to A now? It's 8 because 6 plus 2, right? I have 6 plus 2, so that would give you 8. And I went to A from B. That's the edge I used to relax that. The next one, I can look at E. I cannot do better than that I already have, right? Because it would be, if I take the path from D to B and B to E, that would be 6, but I already have 4. So I'm not going to worry about some of the edges. What about C? Can C be better? No, right? From B, I cannot do that, right? Any questions there? Okay, what's the next thing to relax? Let me just circle those things that were already relaxed. So it's going to be C. So from C, I can only try to relax either A or E. From C, can I relax A? No, you don't have anything to A from C. Can I relax E? I have a 1. Can I relax E to get better than 4? I'm coming from C, right? So C, I cannot do that because I already spent 5 to go to C. If I add another one, that will be 6. So I cannot do that. So I'm done. Okay. So the next thing to relax would be the next minimum. That would be 4. So I take E and see if I can now, since E is like a sink, nothing is going out of that. I'm done. Okay, so these are going to be the shortest distances. And if I draw the shortest path tree, it would look like this. The shortest path tree contains this edge here, AB, and BD, and CD, and ED. Okay, so it's called a tree because if you draw it like this is D, and then from D I can go to C or B or E. From B I can go to A. And these distances are clear, right? And you have E is 4 and B is 2, and this is 5, and B to E is 6. That shows you how the tree gets built. Okay. All right. So the implementation of Dijkstra'S is going to be using a min heap which has log n. Log n is the number of vertices, insertions and deletions. Then you need to have a distance to an edge to, and you need to have a graph to data structure. And the basic idea is, as we discussed the other day, we relax an edge by this is a big O of 1 function because it has no loops and just doing some constant amount of work. But if you look at this one here, there's a loop here that is going through a priority queue. So that would be going n times. But every time it's going through that, you're going to be doing some kind of a delete min there. The next question is, Dijkstra'S algorithm is based on which paradigm? Okay, so Dijkstra'S, the correct answer is A. We call that a greedy algorithm, and it's a class of algorithms in computer science that takes the greediest solution. In other words, it will look for a local optimum, look for the best choice you can get without having an understanding of the global optimization. So amazingly, Dijkstra'S algorithm works because sometimes greedy algorithms are not the best. Imagine that you're trying to go up the mountain and you take the easiest path, the greediest one, but that might not be the best way to get to the top. Okay, but in Dijkstra'S algorithm and many other algorithms, the greedy option works. So it seems to be optimized and it seems to work well. A backtracking algorithm is essentially what we discussed with the maze algorithm, solving a maze. Dynamic programming is something you might learn in the future. That's another programming technique to bring down some of the exponential time algorithms to more polynomial time, more control. And then there's divide and conquer algorithms such as a Quicksort or binary search. Okay, those are called divide and conquer. Okay, our next topic is going to be the sorting, and we'll talk about insertion sort. Let's say we have some array like this. Okay, so let's take the array 3, 1, 5, 2, 5, 1, 2. The way the insertion sort works is that, get more room here. Okay, the insertion sort works like this. It'll start to try to insert. So it'll go 1, 3, and then it'll try to insert 5 into that. So it'll go 1, 3, 5. It'll try to insert 2 into that array. So every time you do this, you're creating a sorted portion at the beginning of the array. So if you do that, then you're going to get 1, 2, 3, 5. So the way you do that is to push things to the right to insert 2. Then you try to insert 5. And because 5 and 5 are the same, we can just stay there. And then you try to insert 1. So if you insert 1, you're going to insert 1 somewhere, either just after 2 or just depending on how the algorithm is implemented. And then you insert 2. And finally, you get the sorted algorithm. Okay, so that's called the insertion sort. The nice thing about this algorithm is just very simple, not too complicated. What we know is that the segment from 0 to I is always sorted for some I. So I kind of changes from I equals 1 to I equals n minus 1. So that's the idea, and you can do all kinds of analysis on that, and it's a very popular sorting algorithm. The merge sort, on the other hand, is another type of an algorithm. So 3, 1, 5, 2, 5, 1, 2. So let's take 3, 1, 5, 1, 2, 5. Let's see, 3, 1, 5, 2, 5, 1, 2, 2, 5, 1, 2. Okay, so let's take this array. This has. Let me add another element so that it becomes nice. So let's put it like this. So if you recall how we did this in 111, we divided this into 2 arrays. So it is divide and conquer, essentially, divide and conquer algorithm. And we have 5, 1, 2, 3. So we take the array of size 8 and divided that into 2 segments. And then we're going to divide this into two other segments. All right, and then we're going to divide this into an array of size 1. Okay, so hopefully you remember all these things from 111 from last semester, maybe. So then the next process is the merge part. So that's the big idea in merge sort, is to merge two arrays of size 1 that are already sorted and get an array of size 2 that is sorted. And same thing here, we merge 5 and 2 and get an array of size 2, which is sorted. Now it's 2, 5. So now we have two arrays of size 2, which are sorted 1, 3, and 2, 5. That gives us one array of size 4 that is sorted. And same thing is going to happen from this side, from the right-hand side, 1, 5, 2, 3, and then it gets 1, 2, 3, 5. So now we have two arrays of size 1, size 4. They're both 1, 2, 3, 5. Once you merge them, you're going to get 1, 1, 2, 2, 3, 3, 5, 5. So we have a sorted array of size 8. Okay. Now, one thing about this algorithm is that we have n things, and we break it up into, you can now relate to this more beyond 111, because now you know about binary trees. Now, what you saw here is like an implicit binary tree that's created out of this process. Okay. And the height of this binary tree is what? What is the height of the binary tree if you have n things? Yes. So the height of the binary tree is log n. Okay, so if you have n things, like for example, you can think of n as 8 in this case. And if you take log base to 8, that's equal to 3. You can see that this is a tree of height 3, a tree of height 3. Okay, 3 edges from top to the bottom. So that's one nice property about the merge sort. It always creates a binary tree of a good height, more like an AVL tree, very balanced. Okay, sorting quiz. Let's do this one here. Okay, so the question is, which of the following sorting algorithms have the worst case quadratic runtime? Okay, so most of you picked A. That's actually true. A is true. So is B. Okay, both A and B are true, and no one picked C. That's good. So insertion sort and selection sort both are bad algorithms. They are quadratic algorithms. Insertion sort is much better than selection sort for various reasons. And so let's ask the next question. The next question is going to be, let me initialize poll here, and we do the next question. So the next question is, okay, next question says, which of the following sorting algorithms require extra memory? I should say linear time memory, order of linear memory. Okay, so the answer is, correct answer is merge sort. Answer C. If you pick answer C, that's good. I think most people did pick answer C. And so merge sort requires the auxiliary array because we have to merge two sorted arrays into one, and that needs this extra array. Both insertion and selection sort don't need, other than just an extra variable, they don't need any extra memory. Okay, so the next question is going to be, okay, let's do, we just get the, 1 second here. Will my memory come back here? Okay, so the next question is, which of the following sorting algorithms is good for small data sets? Okay, that's going a little bit slow, but the correct answer is insertion sort. In fact, insertion sort is the best algorithm for good for small data sets. Because I think that has the lowest amount of overhead or the opportunity for worst case performance when you have a small data set. So insertion sort is the correct answer here. Okay, so the last question, let me initialize this. Okay, which of the following sorting algorithms is good for data sets that are almost sorted? Okay, so it looks like many are choosing selection sort, but the correct answer is insertion sort. If you recall the insertion sort, the idea is that if, like, say, you have a data set that is, let's say, almost sorted like this, or just have just a little 6 and 5 are in the wrong place. There's nothing to do 1, 2, 3, 4. You don't have to do anything. 6, you don't have to do anything. But 5, you need to push to the other side. So when the data set is already almost sorted, insertion sort does linear amount of work to sort it. So the correct answer is the insertion sort. If the data set is almost sorted. In fact, in practice, a lot of times, an algorithm might choose to do insertion sort, even if it can use an n log n algorithm. Those algorithms only make sense when n is large. But if n is small, there's no reason to use something like merge sort because there's too much overhead in recursion. Okay, so finally, we're going to just do a basic sorting algorithm comparison. So we'll look at 3 algorithms. There's another algorithm called heap sort, which I didn't really discuss, but we will discuss that next week. The memory required for both insertion and selection is just constant amount of memory, just 1 or 2 variables. Okay, and the for the merge sort, it requires some linear amount of memory because you need to have extra array to do things. And the best case for insertion sort is linear. That is when the array is almost sorted. The average case is n squared, and the worst case is also n squared. For the selection sort, all 3 are n squared. Because in selection sort, if you recall, you have to find the min or max and do an exchange. And you have to do that n times. So if you find min, which takes n time, and do that n times, you're always going to do n squared time. For merge sort, it has a very consistent performance with log n performance for all. In fact, if you use Java sorting, Java API sorting algorithms, they are mostly implemented with merge sort to guarantee, oops, not log, it's just n log n, sorry about that. So the merge sort is n log n. So that's what the idea is. Okay. So now we're going to talk about something new. This is called the Quicksort. This was invented or developed in 1960s, a long time ago, and it stand the test of time, and no one has been able to come up with a better sorting algorithm than Quicksort. Although this was developed in 1960s. The person who invented this algorithm, he's a British person. He got a knighthood for inventing Quicksort algorithm. So it's had its impact. That's why he was given a knighthood. So he's Sir O'Hare. So the basic algorithm, Quicksort, is called a divide and conquer algorithm for sorting. The idea is to partition an array into 2 parts, and then sorting the parts independently. So essentially, it works with an idea called a pivot. The pivot is some number or something, and there's a property of the Quicksort that indicates that anything to the right of the pivot is greater than or equal to the pivot, and anything to the left of the pivot is less than or equal to the pivot. Now, clearly, if the elements are distinct, then we can use strictly less than or strictly greater than. So that's the basic idea of the thing. And you might ask, why is this going to sort an array? That's because after you do the pivoting or partitioning, the 25 is in the right place of the array. That's the goal. I think you will see some examples of that. So here's an example. Let's suppose that we take the input, which is an array of characters, which characters are quicksort example, but those are the characters. And one of the first things you do is you shuffle. You shuffle this array so that it doesn't have any bias. Because if there's bias, quicksort can perform quite badly. After you shuffle, then you would bring some element to the front. We don't know which one, but you do a shuffle, you do a random shuffle. And that element is called pivot. And so the goal in the partitioning stage is to put the pivot into the right place of the array. So essentially, pivot goes to where the L was before that. And then what you should notice is that all the elements that are bigger than the pivot, bigger than K in alphabetical order, is to the right of the pivot. And all the elements that are less than or equal to the pivot is to the left of the pivot. Okay? And what you get is now two arrays, which is this. And so we essentially recursively apply the same idea to those arrays. So we have a left array and a right array that are not sorted. But we can recursively do the same thing. We again pick a pivot. Let's say we pick the pivot A, which is a bad pivot, because if you split it, if you partition it, all the elements are to the right of A. And so you don't really get much of a partitioning. The goal is to break it in the middle, somehow always get the middle element to as the pivot, which is not always going to happen unless you can find the median of the data set, which is expensive to do. So the goal is essentially to get a good pivot by randomizing and somehow split it, partitioning, and get that. So for example, if you pick the pivot to be E for the next partition, as you can see, it's partitioned now into two arrays, and the E is in the right place. E shouldn't go anywhere else. And now I can recursively apply quicksort to the other partitions. Okay, so quicksort, the major idea is the partitioning step. That's what the quicksort major idea is. Yeah. Okay, so quicksort is very popular for a variety of reasons, because it's not difficult to implement. So you might imagine that you have to write a partitioning algorithm, and then it's just recursion. And in fact, quicksort is very short. Just like, in the merge sort, you do merging. That's the big idea. In quicksort, the big idea is partitioning. And in practice, it works well for a variety of different kinds of input data. So as I said before, it's very popular sorting algorithm to use for many things in practice. It is substantially faster than any other sorting algorithm for typical applications. In other words, if you have a data set which is randomized, it works really well. And it's in place, meaning that you don't need to use extra memory like the merge sort. And also it runs in n log n time. Now, this n log n time, I think just an intuition for that is essentially the goal of the quicksort is somewhat very similar to the merge sort. You do partitioning, and then you partition within partitions. And so if you'll get lucky and find the right element to partition, in every step you get equal size arrays. And if you do that, if you keep dividing something by half, you have a tree of height log n. So it's a same argument can be used to a partitioning step takes n work, just like the merge step in merge sort. Okay. All right. So let me show you sort of like this step. Yeah. So this picture kind of shows you what the quicksort does. You pick a pivot and you so that all the things, so in the middle of the algorithm, your low has come here and your high has come here. So they're kind of merging, low and high. Just like if you recall the algorithm for binary search, we did the same kind of thing. And the goal is that what's in the middle is not determined yet. We don't know what's happening. But at the end, after one partitioning step, you have your pivot in the right place. So you always exchange when the low, I mean, you can keep the I and j and low and high, but let's do an example here. Okay. So we will try to partition the array. Easy question. Not an easy question because we're just learning this. So what is the pivot we want to choose here? Let's assume that we're not going to shuffle anything. So what would you choose to be the pivot? Yeah, so in practice, you always choose E to be the pivot, the first element to be the pivot. It can be anything. You can randomly choose anything. But even if you do it algorithmically, what you have to do is to, I think one thing you can do is to randomly pick something and then exchange with the first element in the array so that you can run your algorithm nicely. So the algorithm works like this. So we have low and high. The low is moving to the right and the high is moving to the left. So the algorithm works like this. This is called the pivot. Okay. So the algorithm works like while the a's of low is less than or equal to the pivot, the low moves forward. All right. So as long as the a's of low is less than or equal to the pivot, it keeps moving forward. So for example, when will the low stop? Which character the low is going to stop? It's going to stop at S, because at S, it's no longer A of low is less than pivot. Pivot is E, right? So A is the only thing that's smaller. And the second loop is going to be while the A of high is greater than or equal to the pivot. we'll do high minus minus. So that means we are moving high to the left. So question is that when will the high stop? Which character the high will stop? High is coming to the left. High is currently pointing to n. While ace of high is greater than or equal to pivot. Yeah. Okay, so someone said A. Okay, good, good, good. Yeah, okay. All right. Let me just change it a little bit here. Just to make it a little interesting, I guess. Let's write that to be strictly greater than. Where will it stop? Yeah, so in that case, it's going to stop here. Okay, at E. And when that happens, what we're going to do is we're going to do the following. When both things stop, we're going to swap ace of low and ace of high. This is the partitioning algorithm that I'm discussing. Okay. So what that means is ace of low and ace of high is swapped. So let me mark them who they are. So after you swap the ace of low and ace of high, your array looks like this. E is still the pivot. And E comes here where the S was. Okay, then you have Y, Q, U, and S goes to, so these two were swapped. E and S were swapped. And then we have S, T, I, O, N. This is how the array looks like. Okay. So right now, the high is here and low is here. Okay, so the next step is really to put another loop on the top of this. It says while the low is, I believe it's less than or equal to, I forgot exactly, but it just keeps running. Okay, so as long as low is less than the pivot, just keep moving low to the right, less than or equal to the pivot. So because E is less than or equal to E, pivot is E, and it keeps moving to the right. And it'll stop low here because now Y is bigger than the pivot. And the high will keep moving to the left because ace of high U is S is going to be bigger than E. So go to the left to U. U is bigger than E, so go to the left to Q. And now Q is bigger than let's say Q is bigger than E, so go to the left. So right now, high and low are both pointing to Y. Okay, and the Y is still bigger, so high will move here. So the high is going to move all the way to the left and stop at E, because at E, it's no longer true, that condition. Okay, so at this point, your algorithm will stop, and the no swaps are necessary because you have everything in the right form. So the only thing necessary is that you're going to swap the pivot with the ace of high. And you're going to get, oops, 1 second here. So you're going to get E, A, E, Y. So that's the pivot, Q, U, S, S, T, I, O, N. So this is the main idea of the quicksort. So what you see is like this portion is not sorted. This portion is not sorted, but the E is in the right place. That means we don't have to touch that E again. And we can now focus on left half and the right half. Okay, let me ask you this question. What I did, this algorithm that I showed you, the partitioning algorithm, what is the big goal of this algorithm? Just partitioning with one pivot. Okay, so I'm getting the answers big O of n. That's correct. If you actually notice this, although we have 3 while loops, we just keep moving to the left or to the right. And high and low cannot go, the amount of spaces the high and low moved cannot be more than n. So we just moved n spaces, the worst case. So in order to partition something, it's going to take n amount of work. Okay, and the next thing shows you the quicksort algorithm. The quicksort algorithm goes like this. You want to sort an array of comparables. We start with a low and a high. So typically low is 0, high is n-1. And if high is less than or equal to the low, we want to return, or you want to stop the recursion. This is called the base case. And the main part, the main workhorse, is the partitioning algorithm, which I just showed you. So you write a function called partition, which will partition the array based on some pivot. So this costs you n amount of work. And then we sort the left and we sort the right. So that means it's again, recursively, we call the same function with the left one and the right one. So you can see how easy this quicksort algorithm is to write. You just have to take care of the partitioning thing, but the main algorithm, just like merge sort, is quite straightforward. You partition the left, partition the right, and in this case, the J is in the right place. Okay, any questions about quicksort? There was a question about, oh, you have to swap these because we don't know what this. In this case, you know, we don't know what the pivot is. Pivot. Only thing we know is pivot should be in the right place, so that's why we swapped. Okay. The worst case for quicksort is n squared, which is true. How is that possible? What data set, what pivot will give you the worst case performance? Yes, so the worst case performance is that, let's suppose that you're trying to sort an array, and we always pick the minimum. So you split it into 1 and then 2, 3, 4, 5. Then you pick 2 and 3, 4, 5, and so on, right? So then you pick 3 and then 4 and 5. So if you're unlucky, if your pivot is not good, if your pivot is biased, like min or max, it could give you a tree height of n, not log n, because for each one you just split 1. And because it costs you n work in every pivot step, all the pivot steps cost you n work. So you cost you n work, but then the height, you have to do it n times because the height is set, not log n. Ideal case would be that our pivot is the median. But that's a hard thing to do. Okay, so something like that. Okay, now let me ask you this question here. Okay, so the question is, here's the question. Okay, so the question is, can we use partitioning maybe I should write. All right, so the question is, can we use partitioning to find the median? But before that, let me ask you this question. What is, oops, hold on 1 second here. I'll just write it. Suppose you're given a random array and you asked to find the median. How quickly can you do that? Okay, someone said n. Can you explain how to do that in n time? So again, we have a random array and we are looking to find median. Even more, I think, if you have a random array, how quickly can you find mode? Yes, someone said n squared. I think you can do it better than that. Someone said n log n. That's good, but how do you do that in n log n? Yes, so that's correct. So we can sort the array. Going to cost you n log n, and find middle. Going to cost you big O of 1. So you can find median in n log n using something like merge sort because it guarantees sorting in n log n. So now the question is, can we use the idea of partitioning to find the median in less than n log n time? Okay, so some people have partition on the middle array index. Doesn't guarantee that you're going to find this in. Okay, so someone comment, wouldn't the active partitioning give us midpoint? Yeah. Can you explain that a little bit more? The quicksort is n squared if you don't shuffle. So if you shuffle, you can, and shuffling only takes you big O of n. So we can avoid the worst case for quicksort by shuffling. Okay, so I think it's a very nice idea. The idea is that we know we can partition in big O of n. So basically what we do is we take the array and partition it. Okay, and so we partition it and maybe you get your pivot somewhere here. And let's say that our array is of size, I don't know, 100. And the pivot went into the location 22, right? Some 22. So where's the median? Yeah, so the median has to be somewhere, couldn't be there, because those elements are all up to index 22. Median is the 50. We're looking for the 50th element, or whatever the middle element. Right? So what we're going to do is then we're going to do this and partition again. That side, just to partition one side. We are not doing recursively. We just completely ignore the left-hand side. Let's suppose now we came up with something like 65 or something. All right, now we know the median is in that place there. By doing this randomly, finding a good pivot, you will get to the right place very, very quickly. All right, and a finite number of steps, and it's a very it's called the partitioning algorithm, which I will talk about it next time. Okay, which you can use to find the median using the partitioning. You can get to the median. Okay, I think we're going to have a short time about stopping now and let you ask questions if you have any questions to ask.